Okay, so as I was saying, these two things here are state complexity classes, which is maybe a somewhat non-traditional notion. So I'll just begin by describing what a state complexity class is at a high level by sort of contrasting it to traditional complexity classes. So just as a sort of very basic reminder, what do we do in complexity theory? We have some sort of decision problem, which means just some, classical question that has a yes or no answer. And we consider, some computational device. This may be any computational model. It may be a classical computer, a quantum computer, some kind of interactive setup. But whatever this device does internally, it produces a single bit as output. And this is meant to be the answer to this decision question up here. And then a complexity class is just some set of sequences of these classical decision problems that require similar resources to solve. So you should always imagine these x1, x2, x3 being sort of differently sized instances of the same kind of problem. And similar resources is something like, polynomial time in the index here or something like this. But now if this computational model here is some kind of quantum computational model, there's kind of no need to restrict yourself to classical outputs or in particular to single bit outputs. And in state complexity, what we look at is sort of computational devices that produce quantum states as outputs. So the sort of question in state complexity is, if I give you some classical description of a quantum state, for example, in terms of a Turing machine that prints out the quantum circuit for generating that state, and I feed this to some quantum computational model, which may be circuits, it may be some interactive setup, it might be some multi-prover setup. What's the complexity of generating, actually like physically preparing this output state? So state complexity class is then the sort of analogous thing to the classical or the traditional setting. It's some set of sequences of quantum states that require, again, similar resources to prepare. Okay, so that's the general gist here. So as you saw from the title, there are two particular state complexity classes that we'll need here. One is called stateQIP, the other statePSPACE. So I'll introduce them in turn. StateQIP informally are all sort of states that I can generate as a quantum polynomial time verifier by interacting with an untrusted, unbounded prover. So more concretely, the setup is that we have some polynomial time quantum verifier down here. And this verifier sort of has in mind a state that they would like to prepare. Whereby have in mind, I mean it has some succinct classical description of that state. Again, for example, in terms of some Turing machine that prints out the circuit to generate it. But even though it has this description here, it may still be hard to actually generate this state, right? I can give you a Turing machine that is going to print out an exponentially long circuit, and then if you have polynomial time, you can't actually sort of run that circuit to prepare the state. In some sense, you know what state you're trying to get, you just can't physically prepare it. Okay, so then we introduced this kind of dishonest, or at least a distrusted, but unbounded quantum prover. Unbounded means they can generate any quantum state that they want, but the verifier doesn't trust that they will generate actually the correct state. And the verifier and this prover can interact quantumly, and somehow the verifier now has to make sure that they can use the prover's power in generating the state, but not be cheated by the prover into generating some state that they didn't want. Okay, so the verifier will produce some output state, and the goal here is that the sigma n should be close to this target state. And then a state sequence rho n is in this class stateQIP if there exists some quantum interactive protocol such that two conditions hold. So this is a sort of standard completeness soundness from interactive protocols. Completeness means that there is some honest prover that is accepted with probability close to 1 in the protocol, and for which the verifier indeed outputs this correct target state. So this is sort of what the honest prover would do. And soundness says that for any prover that is accepted with at least some probability, let's say 1/2, the trace distance between the actual output state and this target state should decay polynomially in n, where n you can just imagine is the number of qubits. It's again sort of indexed by size as in the classical case. Okay, so that's what stateQIP is. Of course, there's a kind of corresponding traditional complexity class here, which is QIP, which is the set of decision problems that you could decide by such a quantum interactive protocol. Okay, so second thing we need to know is what statePSPACE is. This is slightly simpler to say. A state sequence rho n is in statePSPACE if there is some space uniform sequence of quantum states, Cn, such that Cn generates the state rho n and only ever uses polynomially many qubits. So if you're not as familiar with circuit complexity, space uniform here means that there is some classical polynomial space Turing machine that prints the exponentially long quantum circuit to generate that state. And also, whenever I say circuit, I mean some kind of like generalized notion of circuit that includes mid-circuit measurements. So the circuit actually can prepare a mixed state as an output. And when we say it uses polynomially many qubits, this allows you to reuse qubits, right? So if you're allowed to measure, you can sort of measure and then reuse that space later in your computation. And again, there's some sort of corresponding traditional complexity class here, which is PSPACE, which is the set of classical decision problems decidable using a polynomial number of classical bits. And this turns out to be equal to BQP space, which is the same thing, but for a polynomial number of quantum bits. This is this sort of classic result of Watrous. Okay, so now we know what stateQIP and statePSPACE are, and as the title suggests, we prove that they're equal. So let me first sort of say what the known results here are. The oldest relevant thing is this famous IP equals PSPACE proof of Shamir. So IP, in case you haven't seen it before, is the class of classical interactive protocols. So all decision problems decidable by a classical interactive protocol. And this proof shows that this is in fact the same as all decision problems decidable in classical polynomial space. And then, a good while later, people started studying these quantum interactive protocols, and in this classic result of Yuen et al., they showed that in fact quantum here doesn't help, right? So QIP is equal to IP and is also equal to PSPACE by extension. And really, when you prove this, right, you only need to prove one inclusion here. You only need to prove that QIP is contained in PSPACE, because clearly QIP contains IP. I can just always send classical messages, right? There's no requirement to use quantum, and this is already equal to PSPACE. So really, this paper here shows this inclusion of QIP in PSPACE. So this is all in the sort of traditional complexity setting of decision problems. What about state complexity? This is a much newer thing to study. But 2 years ago, Rosenthal and Yuen showed that, in fact, stateQIP contains statePSPACE. And this you should kind of think of as the state complexity analog of this result of Shamir, because here also the hard direction is kind of this inclusion that IP contains PSPACE. And in fact, this protocol for showing this is a kind of version of this run in superposition. Okay. Right, and now our work does what you would expect sort of from this slide, which is just prove the reverse inclusion, right? And then, of course, you can combine them and show that they're equal. So just as this one you can kind of think of as the state analog of this IP equals PSPACE, this inclusion is kind of the state complexity analog of this QIP is contained in PSPACE proof. So just to say this in words, because there are like a lot of inclusions here, what do we concretely need to show if we want to show this inclusion? We need to show that if I give you any stateQIP protocol that produces some output state, you can find a space uniform family of quantum circuits that use polynomial space and produce the same output state as that interactive protocol. Okay, so we need some kind of way of converting these protocols into these space uniform circuits to generate the same state. Okay, so since this is the state complexity analog of this QIP contained in PSPACE, the natural thing is to look at this proof and see whether it somehow generalizes to the state complexity setting. And it does to some extent, at least the high-level idea does. So at a very high level, what this proof up here does is it kind of takes a quantum interactive protocol and rewrites it as a particular SDP, with the property that the optimal value of that SDP indicates the acceptance probability of a prover in the quantum interactive protocol. So we use a kind of similar SDP-based idea, but the key difference here is that in this traditional complexity setting, we're just interested in a single output bit. You can use a classical SDP solver to compute the classical optimal value of the SDP. And this allows you to use all sorts of sort of old school circuit complexity results. But in the state complexity setting, the output that we want is an actual quantum state. So we can't just use some classical solver on some SDP and that's just not even, it doesn't even type match, right? So what we do instead is we sort of have some quantum SDP solver which actually sort of physically prepares a feasible solution to such an SDP as a quantum state. So what I mean by that is it prepares some quantum state whose density matrix is a feasible solution to that SDP. Okay, so I want to explain a little bit more how this sort of QIP protocol to SDP sort of conversion goes. This is not really new to our work. It's from this older work, but it's really worth understanding, and it's kind of nice. So let's look at this. So if you look at a QIP or any like quantum interactive protocol abstractly, you can just view this as a bunch of quantum channels sort of wired together. Okay, so up here I have the whatever action the prover would do in the first round, and down here is whatever action the verifier would do in the first round, and so on and so forth. So this register here, you should think of as like the prover's sort of private workspace register. It will do something, it will update its private workspace and then send a message. So this is the message register over to the verifier, and the verifier also has some private workspace register. It does some channel, sends back a message, and so on. Because you can always describe a quantum interactive protocol like this. And now you can go ahead and say, okay, let's look at all of the intermediate states. So, for example, like this would be an okay, I'm not very good at the laser pointer. This would be an intermediate state here, right? It would be the state sort of after the first prover map, but before the first verifier map. And you can write down the constraints that these intermediate states have to satisfy. But because we don't have any control of the prover's private workspace register, we can only do this for the reduced state on the verifier register and the message register, which we do have control over, right? We at least know their dimensions, for example. Okay, so what are these constraints? Firstly, going from here to here must be done via this particular verifier map. And the verifier map is something that we explicitly know, right? We can come up with the verifier, so these maps down here, the verifier maps are fixed. And if you write this sort of in equations, it means that this rho m I prime wi, which would be the state here, must be generated from this input state by application of the verifier map. The second constraint that you get is that the prover's action cannot have any effect on the private workspace register of the verifier, right? Simply because it's kind of clear from the picture already, right? So what this means in equations is that if I take a sort of intermediate state here, let's say this one, and I trace out the message register, so I just look at the state on the reduced system W1 here, then this must be the same as if I had taken the state after the prover had applied it. So this would be this state and traced out this updated message register. Okay, so these are kind of the more interesting constraints, and there are two kind of boring ones. You should use the correct initial state. Let's say it's all 0, and the prover should also be accepted with sufficiently high probability. Let's just say 1. So this that Z register here would be like the verifier accept reject flag. Okay, so these are just a bunch of constraints that any set of intermediate states of this protocol has to satisfy. But now what you can show is that, in fact, this is not just a sort of necessary set of constraints, but it's in fact sufficient. So what this means is you can sort of combine all of these constraints into one big feasibility SDP, which just means you have some channel and some matrix. You get this from sort of direct summing the ones on the previous slide, such that if you have any feasible state in this feasibility SDP, so any state rho that is a tensor product of these reduced intermediate states, such that phi of rho equals this matrix B, then there exists a prover behavior that actually produces these states as intermediate states. Okay, so this is kind of the other direction, sort of showing that the intermediate states must satisfy these constraints. You show that any sort of state that satisfies these constraints actually corresponds to the intermediate states for some prover that you can construct. Okay, and this is nice because we included as a constraint that the prover should be accepted with high probability, and we know how to deal with this, right? This is the stateQIP guarantee. So once you know that you have a prover that is accepted with high probability, you know that the target output state is sort of in this final register here. Okay, so really what we need to do is we need to have some quantum algorithm that takes such an SDP and actually physically prepares a state that is feasible. We do this in a sort of slightly more general setting, not for that particular SDP, but for what we call PSPACE-computable SDPs. So these are SDPs which are exponentially large in terms of the channels and matrices, but they're PSPACE-computable, which we take to mean that for a matrix, this entry function from the indices to the matrix entry is computable in classical polynomial space. And a sort of PSPACE-computable channel or super operator is just one where if you have a PSPACE computable input, then the output is also PSPACE computable. So this is some kind of space complexity restriction on the phi and the b that specifies the SDP. And then it's sort of fairly straightforward to show that if you take these particular SDPs derived from the stateQIP protocols, then these are PSPACE computable roughly because they only depend on like the verifier's maps and some like simple things like partial traces, and you can do all of this in PSPACE. Okay, and then sort of the main technical theorem that we show is that, in fact, if you have any such PSPACE computable feasibility SDP, then this has feasible states, so states that satisfy this requirement, that are in statePSPACE, meaning that you can generate them with these uniformly generated polynomial space quantum circuits. So just very briefly, what are the main proof ingredients here? It's some sort of like custom variant of the standard matrix multiplicative weights algorithm. And then we implement this using this block encoding framework of Yuen et al. With this sort of slightly weird twist that we use exponential degree polynomials everywhere, which is a terrible idea if you care about time complexity, but you can do it in polynomial space. It just takes exponential time, which is, it's fine. Okay, so once we have this, this solver, which is entirely impractical, then you get the main result, sort of straightforwardly, namely that stateQIP is in statePSPACE. So just to recap the sort of main steps here, what do you actually do? You start from a stateQIP protocol, you rewrite it into this PSPACE computable SDP, then you use this block encoding based algorithm to actually prepare a feasible state of the SDP. And then you have this guarantee that any feasible state of the SDP must, in its last register, have the correct output state of the stateQIP protocol. You just trace out everything else, you keep that last state, and you've prepared the state that you wanted. Okay, so let me wrap up. The sort of most high-level thing that I hope you're taking away from this is there is this thing called state complexity, which is a kind of different new notion of complexity, which I think is very much underexplored. And there are sort of many interesting open questions in this direction. The thing that we show is that stateQIP is contained in statePSPACE, which then, together with this earlier work by Rosenthal and Yuen, shows that the two are equal. We also show one additional result, which I won't have time to describe in detail, but if you have any sort of quantum interactive protocol, we only ever make sort of statements about the verifier. We don't care about actually implementing the prover, but you can still ask what is the complexity of actually performing the prover operations, right? It's not clear that just because the verifier can decide, say anything in quantum PSPACE or something, that the prover also can be implemented in that same complexity class. But what we show is that if you have any such interactive protocol, then an optimal prover can actually be implemented in quantum polynomial space. And this goes via some kind of more general theorem on the complexity of performing the unitary that relates equivalent purifications to one another. So a consequence of Ullmann's theorem is that if you have two purifications, you can relate them by acting unitarily only on the purifying register. And what we show is if these two purifications are both in statePSPACE, then the unitary relating them is sort of in what is called unitary PSPACE, which is a kind of unitary version of statePSPACE. Okay, the main technical result underlying both this main result and this additional one is this quantum polynomial space algorithm for solving these PSPACE computable SDPs. And let me also mention some open questions here. So if you're familiar with the QIP equals PSPACE proof of Yuen et al., one sort of step in this is that they do this round reduction procedure for reducing it to 3 rounds. And this is like a very nice thing that they do in the proof, but it's not clear whether it actually works for stateQIP protocols. There are all sorts of like weird technical things that come up. So it's unclear currently whether you can reduce this from a polynomial number of rounds to any constant, or ideally 3. I already mentioned this idea of unitary complexity, which is not the complexity of preparing a state, but the complexity of actually physically implementing a unitary. And there you can define a similar notion of unitary QIP and unitary PSPACE and ask, are the two equal, just like in the state complexity case? No inclusion is known in either direction currently. This seems much harder because you can't use all of these sort of state-specific tricks of block encodings and so on. And finally, and maybe sort of more vaguely, we just have a very poor understanding of the relationship between the kind of traditional complexity classes and the state complexity classes. So kind of one crisp way of saying this is, suppose I just assume for the sake of argument that everything is in polynomial time. Does that mean I can prepare any state in state BQP? We just don't know. So there are all of these sort of questions on the interplay between these two, and I think there's a lot to explore here. All right, so thank you very much. Sorry? Oh, you need the mic? Okay.
Hello. Hello. Okay. If there are questions, please shout.
Oh, now
it's working.
Is there any hope of using similar techniques for multi-prover interactive proofs, like say a stateQIP?
That's a good question. I'm not sure. I mean, there's... Sorry, Alex.
So our related question is stateQIP with classical communication.
stateQIP with classical communication? I'm not even sure what that means.
It's so problem in QIP, so you can have classical communication, but at the end of the day, you have to compute the common state.
Wouldn't that just be like you have a classical PSPACE oracle?
I don't know.
Okay, it seems like it would be, but we have to think about it. So to get back to your question, yeah, I'm not sure. It's a good question. I don't think anyone has studied these multi-prover versions of the state complexity. I mean, there's always hope, but I'm not sure how well informed it is as a hope. Yeah, so.
So great talk. Just a very quick question. Are you basically studying like the analog of function classes? Should I think of it this way, like quantum function classes? Is that right?
Yeah, so that's one way of looking at it. You can, I guess function classes are one way. You can also view this as a kind of search problem where like, okay, I actually want to like find the witness. Related to this, there's this very nice paper by Irani and Nirka Natarajan and so on the sort of difficulty of search decision reductions, which kind of like at a very high level, what it tells you about this is that just because QIP equals PSPACE is true doesn't mean that you can sort of say anything directly from that about the state complexity case, because it's a kind of quantum search decision type question.
Yeah, hi. Could you expand a little bit on the difficulty of talking about unitary QIP and unitary PSPACE? Like, are there not sort of simple, I know it's probably not simple, but like state channel duality results, or maybe just, I know that in block encoding, you can often block encode representations of channels. And I'm wondering, I guess, yeah, if you can talk about the stumbling blocks and that extension.
Yeah, so I'm not sure there's like a super good intuition for why it's hard, except that people have tried and failed. Like part of the issue here seems to be that, so what you need to do in unitary complexities, I give you a state, I just give you one copy of that state, you need to apply the unitary to it. So you can't do sort of like things like just, you know, try many times and so on, and it's also not clear how you would use the block encoding stuff to do it. But I don't think there's a very strong intuition. It's closely related to this old unitary synthesis problem of Scott Aronson. But I guess that's sort of all there is in terms of why it should be hard.
So yeah, we are a bit over time, so maybe this next speaker can go and can have an extra question.
Thanks. So with regular complexity classes, you have this notion of reductions between problems. So like one question is there an analogous notion here? And if so, then what would be like, is there a natural complete sort of problem for these classes?
Yeah, so that's an excellent question. I think this is something we're currently kind of doing, but it's not quite as crisp, and it's not like obvious what complete would mean here, right? It's like, is it like I prepare one state, I can apply like some simple operation to get the other? It's just not as clear as in the classical case. Sorry, I hope you can still hear me. I'm not sure.
Sorry, so questions offline maybe then.
All right, thank you.